Should I initiate video?
Or without you on this camera, so just share your screen.
Well, I begin the topic.
Yeah. That works. Can make it disappear. At the end, so small. First, audio, remove video, yes. And one more time, the last one. Control is the, there you go.
Okay, so let me present you, give you some overview of the cost action. This is CA18108, quantum gravity phenomenology in multi-messenger approach. Well, this action started on 14th of March of 2019, and cost action has a duration of 4 years. So this means that it will end on March 23. So, which was the objective, no? The main aim that the action wanted to address. So, you see, it is investigate possible signatures predicted by quantum gravity models in the observation of different cosmic messengers by creating the conditions for a close collaboration between theorists and the various experimental communities involved in the detection of such cosmic messengers. So, you see, this is a footprint or main characteristics of the action. It involves several communities. Yeah, several communities. We have the community of gamma ray astronomy, we have the community of cosmic neutrinos, ultra-energy cosmic rays, gravitational waves, and then we have theoreticians. And the cost action allows this community to exchange ideas. So it is very appropriate, in fact, for what a cost action is. So we have 28 what they call cost members, essentially European countries participating in the action. The countries in the cost action are divided, and the European countries are divided into two groups. One of them is called the ITC, the Inclusiveness Target Countries group, that is essentially countries from the eastern part of Europe, where cost action want to support the research development somehow. And so we have 13 of these countries in the action and 15 which are non-ITC. And then we have also what they call two near neighbor countries, which in this case are Russia and Armenia. Apart from this, researchers from international countries can also participate in cost action. In fact, we have people from 10 what they call cost international partner countries. This is going to change soon because from 1st November, new cost rules enter into play, and in this case, in fact, all cost members, all countries, no, which are cost members, will participate in every cost action. I mean, this will no longer be the case anymore that we only have 28. No, in principle, all countries participate in every action. And with these rules, every researcher of a cost member will be able to ask participation just from the web page, the main web page of the action. But this is something new, and so I'm not going to go into that.
Sorry, we did this for applying for cost and do any, but it's up to you.
If they?
And they do many countries in the world.
Yes. No. So researchers which are from a non-cost country, that is international country. So before 1st November, I mean, as of today, they had to ask to be incorporated into the action by a special administrative procedure. This involved to fill a form and saying exactly the advantage both for this country and for the action of the participation. No? And this had to go first under approval of the management committee and then also under approval of the cost association. So this was a rather bureaucratic and long procedure, but this is going to change. So until now, people from these countries, they were called MC observers, but as I said, this will be different. In fact, people from international countries will be able to ask participation in the action exactly as in the same way as people from European countries, just asking from the website, and then it is the management committee of the action who approves the participation. This does not mean that people from or researchers from international countries will be able to get reimbursement, for example. This is more or less the same as it is now. As it is now, only researchers from cost members countries can get reimbursements, and people from international countries they need to have their own finance. There will be some small changes. For example, I think the rules are not completely definitive. I received some preliminary document, but it seems that people from international countries will be able to be reimbursed only only for one event in the whole lifetime of the action. But once they will be able to get this reimbursement. Sorry, I cannot hear you very well.
You have to have a certain number of countries that are represented, right? In the action.
Yes.
And those being non-European or
No. The management committee, you mean in the management committee? No, the management committee is the main body of government of construction, and at present, for example, there are 2 representatives in the management committee for each of these 28 coast countries. And researchers from international countries, they can participate in management committee as observers. And this will be something similar also in the future. There will be also some changes because at present there are full members of the management committee and substitute members. For example, in the future, there will be only full members. And when one member cannot attend an event, for example, he's able to nominate or to be substituted by another researcher from the same country participating in the action. So these are the new rules. Yes. Yes, exactly. These countries refer always to the country where the researcher does his work. Okay, so in our action, the coordination is made through different working groups. This is the usual structure of construction. In particular, in action, we have mostly theoretical theoretician working group, which is working group 1. But it is a theory group, but always focused. Well, Christian will explain a little bit in detail after me. Focused on the phenomenology, the models to extract some phenomenology. Well, there is also a working group, which is working group 2, which tries, in fact, to do this bridge between pure theory and the experimental community. And then there are 4 groups which are devoted for each of the cosmic messengers. So here, this is the core group of the action, which is formed by the action chair, the vice chair, grant holder, scientific representative. The grant holder institution is IFAI in Barcelona. Science communication manager, what is called the STSM coordinator. I will explain a little bit what is this STSM, and this ITC conference grant manager. And then there are working group leaders, 2 of them for every working group. Here we are here, Christian Pfeifer here, Julia Gubitosi, and Tomislav Terzić over there. From this group of people. We have a number of information channels. We have our website. I will show you this in a minute. We have Facebook, Twitter, Instagram, also a Telegram channel about related news. Well, we will see all these tools that they are shown in our website. So, which are the activities? The activities are always done through what the cost action called tools, no? Activity tools. The first one is activity that may be of interest to you. It's what is called short-term scientific missions. It allows a researcher from one country to perform a research stay in another country. I think there is a minimum duration of I don't know if it is 1 week or something like that. And in principle, I think there is no maximum duration of this, but there is a maximum on the well, one requests some financial help for this special, and there is a maximum for that. In any case, we publish from time to time calls for this STSM. Another tool is the ITC conference grants. This tool is for researchers at the PhD and the early postdoc level from ITC countries to attend conferences that in principle are not organized by the action. And we have, there is the training schools, and this is our first training school. Our plan is to have at least one, perhaps the original idea was to have 2 other training schools, but well, because of the pandemics and the situation of how the specific duration of the action can be modified, it's not clear that we will have a third one. But in principle, there will be another training school. In fact, the next year is also fixed, will be in Serbia. And it will not be a repetition of this school. It will build on what we are learning in this school towards more advanced topics. This will be the idea. So we have had also some meetings. There is money to meet. We had a kickoff meeting in Barcelona, and then our first annual conference in Granada, and the second annual conference is going to happen here in Corfu. And we have also some online meetings during the pandemic, but perhaps Christian will talk about this. We have a number of outreach and university activities. We have a very active outreach group, and you can see some of the activities in the website, but also following the social networks, the social media. And one of the main tasks that we have been doing during the late times, especially during the pandemics, is the elaboration of a review of quantum phenomenology, which is well, it is produced. It will be a product of the action. Not every action participant, but is a writer or an author of this review. But in fact, there are many of them. Will be more than 100 authors. So we are finishing this review. It will be completed during October, and will be published in Progress in Nuclear and Particle Physics. Okay, so I'm going to show you just the website. The problem is that I will not be sharing this. So perhaps, well, okay, people from attending online can try to click on this website. I'm going to describe simply. There is the main page here. The main page, you can see the goal of the action. This is what I was saying in the first slide. But you see here, there is also a second objective. It is the formation of a generation of scientists that will be competent in the interdisciplinary expertise that is needed in the effective search of quantum gravity footprints. So this is precisely what we are doing now. This is the objective of the training school. You can also take a look here at the Memorandum of Understanding of the action. This is the document where, which was approved by the Coast Association, and where really it is described which are the main objectives of the action. In fact, you can just read a little bit. For example, research coordination, to clarify some apparent contradictions obtained in different analyses of experimental data produced by different messengers, or to systematically derive constraints for the different theoretical models from the experimental results coming from different messengers. Well, you see, there are some research coordination objectives: to develop new strategies, optimize existing ones for performing studies of quantum gravity effects, to convert the efforts of separated research groups in a common and well-defined research strategy, and what they call also capacity building, which has to do, for example, with the formation of scientists that we were talking about. So you can take a look. You want to know a little bit the background, to have some background on the action. Then there is the description of the challenge, the description of the objectives, some description of the state of the art, etc. Okay, so you have this documentation there. If we come back to the web page of the action, there is an about. Well, there's some news we collect here. Of course, a little slow, but I mean, you can subscribe to this news and receive them. There is also all participants in different working groups are listed here. These are the calls that I was mentioning. For example, the STSM call. If I go here, you see there have been 3 calls until up to now. And we have had, in fact, we have had, before the pandemic, we had 3 STSMs. During the pandemic, we had several of them that were cancelled, of course. And then during the last month, I think we have had another 3. Okay, here the events, both action events and related events also. Okay, and perhaps here under tools, well, we have also a shared Google Drive. We put some documentation, and we have been using it extensively for this review. The link of this one of the projects of the action is a database with this multi-messenger constraints. Well, and here you can see also some of the outreach activities, all these social media we have and different outreach activities. Okay, there was here a joint tab with an application form, no, to belong to the action. Well, this is going to be discontinued because, as I said, this is going to be treated differently from personal member. There will be a special in the main site of the action, because this is our website. But if you go to home, there is also a site for the action that belongs to the main cost site, which is this one. So this is the cost website, and pointing to our action. And here there will be, this is there will be yes, also a tab or a button to apply for participation in the action. So this will be the way to apply for the action. Okay. So I just wanted to say a few words on the kind of problems, no, that I'm going to go very quickly with this because well, this is something that we have been seeing this morning in the lectures. Okay, you know that we have these four cosmic messengers. You know, the protons, low energy protons get deflected by magnetic fields. High energy cosmic rays, in fact, they can go directly, but they may interact with the cosmic microwave background. Instead, we have photons that really point to the original cosmic accelerator, but as we learned this morning, and also in some will tell tomorrow, these photons, high energy photons, interact also with the background. So there is a limitation on the distance the photons can perform and the corresponding surface. This, of course, doesn't happen with neutrinos, but with neutrinos the main issue is the difficulty to detect them. And we have the gravitational waves, the new messenger, new window that allows you to give a good estimate, for example, of distance and type of surface. So you see, this is four possible astronomies, but they are complementary, so that they allow for possible multi-messenger analysis. Now, the idea of this phenomenology of quantum gravity is that during the propagation, there may be some effects due to quantum gravity. And these particles, well, in the case of gravitational wave, they are particles, but they might be also affected by some quantum space-time or space-time form. Of course, this possibility to have a non-standard propagation, a non-standard space-time, is a small effect. But this effect is accumulative because they propagate long distances. No? So this is why this is a window to the phenomenology of quantum gravity. And of course, we use different type of detectors for these messengers, like the Imaginary Cherenkov telescopes, Elisa showed this morning, that can be complemented with satellites, and of course, for the future, the Cherenkov telescope array. In the case of cosmic neutrinos, we have a very large detector, which is IceCube. So you see here, for example, these are Eiffel Towers. No? You see here the magnitude of how these optical are buried inside the ice in the Antarctica, and this allows to detect a cosmic neutrino, which is coming through space. It reaches the Earth, it reaches the ice of the Antarctica, and then it makes an interaction with a nucleus in the ice, and this interaction produces an energetic particle that gives a Cherenkov light that is detected by these optical modelers. So in this way, you are able to obtain a signal that allows you to reconstruct the energy of the original neutrino and this direction. For example, this is one of the large highest energy obtained. It's called Big Bird. Big Bird is with this comes from the Sesame Street. No, it is just because before this one there was other two new high energy neutrinos larger than 1/5 that they were called early and early. And of course, for ultra high energy scale, we have these very large arrays, telescope array in the northern hemisphere, the Kiroli Observatory. In this case, 3,000 square kilometers. Also, because the flux is really low, no? in the largest part, highest part of the tail, one cosmic rays per century per square kilometer. And of course, they detect, they are sensitive to this, all the air showers that are produced by these primary cosmic rays. And we have for gravitational waves, these gravitational wave detectors, LIGO, 2 hours of 4 kilometers each, or Virgo, where you have some mirrors in both sides and a laser which is bouncing between these two mirrors, and when passing under the passing of gravitational waves, there is a time delay between the lasers that goes through the scope of the arc, and you see a signal. Okay, so you see these are very different detectors, and the experimental community is also has an expertise in each of these physics. So the idea of the construction was to put all these communities together and also talk with the theories what they are expecting from them to look at. Just a few examples very quickly, because my colleagues are going to talk about this. The normal or the usual quantum gravity phenomenology is based, for example, in a modification of dispersion relation, which gives you a modification of the propagation of these particles. One considers that at energies below the Planck scale, one can have a footprint even if one can neglect gravity. In discarded gravity, still there is a footprint at low energies. And this is modeled with this term that is, of course, very small, especially if n this power is large, but that the effect can give you an effect that is really important, because this effect can happen with the distance. You see here the delay, which is proportional to the distance. And in fact, with photons, with high energy photons, we may have sensitivities to the Planck scale. That is, in the case of n equal 1, to have a sensitivity to this coefficient, which is of order 1. The sensitivity is worse for higher n. Of course, as I said before, one is limited with gamma rays because they interact, gamma rays interact in the background. So one could take a look to high energy neutrinos. And there has been already in the literature claims about some time delays coming from or attributing them to the same sources. So this kind of claims, in fact, are controversial and are also under discussion and scrutiny by the action. Another example with ultra high energy cosmic rays is the threshold effects. For example, in the lectures, I'm sure she will speak about the cutoff. Very high energy protons can interact with cosmic microwave background, and well, this process has a threshold. It only is produced for an energy higher than this threshold. But this threshold can be modified by these new dispersion relations. And the new dispersion relations can even make that the threshold, disappears completely, or can make the threshold go to lower energies. So from constraints coming from what Auger seen, which is an ending of the spectrum, one can get very strong constraints. Now the problem is that apparently there is a large sensitivity here to Lorentz violation, but of course, if one sees an end of the spectrum, one should ask whether this is a GCK cutoff or perhaps one has some effect on the source, a lack of accelerator for such a high energy. So this is something typically here. And just a final example with photons. The photon is a stable particle, but if you modify the dispersion relation, then it can disintegrate in vacuum and produce an electron positron pair. Of course, this is a process which is forbidden in special relativity. You have this relation from conservation of energy momentum that cannot be satisfied because the energy is always higher than the momentum, and then this sum cannot be zero in special relativity. But if you modify the dispersion relation, then the reaction gets allowed, and there is a threshold. this effect also happens with neutrinos. Neutrinos in the propagation with Lorentz manipulation can also produce electron-positron pairs or the process of neutrino splitting. Now, my only remark is that Lorentz manipulation has been studied a lot in the past decades, but when one has this phenomenology, one could ask the question of, okay, if Lorentz is no longer a good symmetry of nature, so you have a modified discussion algorithm, but what is the system of reference when you are doing physics? So, in principle, Lorentz manipulation means a privileged system of reference. In fact, this is not the only alternative. There are also extensions of special relativity where the symmetry of special relativity is not violated, but it is deformed, it is modified to another symmetry. And this goes under the name of doubling special relativity. We will have a lecture on that in the final end of the school, and also you guys are going to talk a little bit about this just as a work. So this is all I wanted to say, to give you some taste about what the action is about. So do you have any question, any comment? If not, I give the word to Christian. And okay, I have to change the.
Thanks, Manuel, for the general overview of the cost action. I just want to give you a very short overview of what we do in work group 1 and work group 2. A lot of people who are members of the cost action in work group 1 are also members of the work group 2, so that's they're not working independently of each other, but in close collaboration. As Jose Manuel said, we have 6 working groups, and these 2 working groups, group 1 and group 2, are focused on the theoretical part of quantum gravity phenomenology and multimassive astronomy, called theoretical frameworks for gravity effects in Planck energy and phenomenology of quantum gravity. Working group 1, the leaders of the working groups are working group 1 are Julia and me, and working group 2 is led by Flavio and Stefan. I just want to give you a very brief overview of what we have done and what we want to do. So the aim of the working groups is to describe scenarios for low energy subplanckian effects induced by quantum gravity theories. So on the one hand, we develop, or colleagues of us and members of this working group 1 develop fundamental theories of quantum gravity, but our aim is to predict possible observational imprints of these fundamental theories of quantum gravity. To do that, very often the fundamental derivation from the fundamental principles is not possible nowadays still, so we need to make some effective models from which we then infer on observational signatures. Yes, and we want in particular to predict observables which then can be seen by the experiments conducted from our colleagues in working groups 3 to 6. One idea, which is work in progress, is to develop a certain parameterization of these effects so that we can say, okay, you have your favorite theory of quantum gravity, then you have a certain procedure how to develop, how to derive observable effects, and then we parameterize them all in the same way. In gravity theories and some modified theories of gravity, there exists a framework called the post-parameterized parameterized post-Newtonian framework where a lot of gravitational theorists agreed on a certain way of parameterizing the effects, and you can measure these parameters and then compare what does your favorite theory of gravity predict for these effects, and immediately see is it falsified or not, and the optimal outcome would be to find such a parameterization for observable effects for the use of quantum gravity. And then, yeah, we want systematically derived constraint and combine them into a consistent picture. Yeah, the idea is to further develop and extend the existing theoretical frameworks, where on the one hand, a lot of members of the working group 1 are working on fundamental approaches to quantum gravity, asymptotic safety, loop quantum gravity, group field theory, string cosmology, causal dynamical triangulation, or non-local quantum gravity models, some of which you encountered also in this group. Then we have a lot of members who work on quantum deformed relativistic kinematics, also relativistic symmetries, like W special relativity, or an extension of that to something which one might call W general relativity. Jose Manuel just mentioned this, and we will also have a lecture on this at the end of the school, and Julia will also talk a bit more about this models. Related to this are non-commutative geometry models, the standard model extension, which parameterizes Lorentz invariance violations. We're looking at modified dispersion relations and geometric formulation of curved spacetime of modified dispersion relations, for which one can use Finsler and Templeton geometry. Colleagues are looking at generalized uncertainty principles and modified gravity as an effective. This is just a summary, or an incomplete summary, of topics where members of our working group 1 and working group 2 are working on. So what do we want to do, and what are on our to-do list, also from the Memorandum of Understanding of this cost action, is to improve the mathematical consistency and our physical understanding of these models, to provide reliable predictions, to find and admit experimental constraints. We want to describe observers and the measurement in the presence of a Lorentz invariance violation in PSR scenarios consistently. In particular, we have to distinguish these scenarios. And yeah, we want to bridge this, these fundamental theories with the sub-Planckian regime, which is accessible in observations. So let me quickly summarize some past, present, and future activities. As Manuel already said, we had some workshops which were organized by the by our cost action, or are related to our cost action, which was, for example, the celebration of the 20 years of the emergence of W special relativity, or a seminar which was focused on the experimental tests and signatures of quantum modified quantum gravity. We are all together working on this complete review of quantum gravity phenomenology, which is submitted to the journal in October. And we had numerous of these short-term scientific missions, which initiated new and ongoing collaborations and resulted in several publications and new insights. Another tool we are using is, or what we want to also extend in the future, is to have regular online meetings on a certain specific topic to discuss recent developments between the workgroup members. So the first discussion round we already had was this LASO online discussion, and we want to extend this into the future. This to be started is wrong, but we already began with this. Yeah, suggestions for further activities are welcome, and this is already it from a short presentation of working group 1 and working group 2. If you have any questions or suggestions, you can always contact me or Julia or anyone else if you have any questions. Questions in general on the cost action, what Jose Manuel said. Yeah, on the one hand, we hope the cost action establishes long-term collaborations. And on the other hand, we will think about I mean, one offspring of such a cost action would be the application for the next cost action, whether similar or related focus. I think, sure, we cannot just extend the existing cost action, but this would be one thing that we connect the community and find a group which starts an approach for the ongoing network, or financing an ongoing network of collaborations, yes. Yeah, exactly. That's one of the goals. Questions? Okay, thank you. We have a short break now. 5 minutes? 10 minutes? Yeah. 5 to 10 minutes.
puzzles still to be solved, but we are quite happy with where we are. Then we have had lectures by Renato that argued that there is actually a quantum problem. We try to put theories together. And in fact, she discussed all the many efforts that theoretical physicists are doing in order to try and find a viable theory for quantum gravity. Then at some point, so you were listening to all these nice theory lectures and theory discussions, and then we started having lectures on statistics from Montgomery. Then today we get astrophysical sources and high energy photons, and tomorrow we are going to get more about other cosmic messengers, gravity waves, etc. And it looks like you get different schools. So you have one kind of school, and then now you are in a different kind of school. And you might wonder what is the point. So what is the link between all of these topics? And I mean, you've heard of this quantum gravity phenomenology, but you wonder, okay, but should I really learn, or should I really become comfortable with all of these topics? Yeah, actually, I mean, the reason why we are here is that we think we need people that are able to move comfortably between the theory and the experiment and data analysis and so on and so forth. So this is our goal. And this is because the general aim is that we build quantum gravity as a field that is not just about philosophical or purely theoretical questions, but we want to turn the field into an experiment-based field. So this is what we hope that, the way we hope science can progress. And we want to be able to do that with quantum gravity as well. And this has not been much the case in the past. Why it has not been the case in the past? Of course, because the scale of quantum gravity from the lectures from the Terzić is a faraway scale, it's a very high energy scale, so we do not have direct access to that regime. So you might say, okay, I don't need to worry about that, and I will never be able to measure anything related to that. But already, for example, from the lectures of Gianluca, where he was describing the universe, already there, we started getting a hint that actually we do have physical setups where quantum gravity is relevant, and one of them is the early universe. And then there is another setup, which is the one probably more closely related to the research done in induction, which is the fact that even we do not have direct access to the Planck scale, we might still be able to see remnants of physics at the Planck scale at lower energy. And this is because there can be amplification mechanisms. So of effects that would be very tiny at low energies. So they would be big at high energies, but we don't reach that low energies. They would be very small at tiny, very tiny at small energies. But we might have an amplification mechanism that turns these tiny effects into something within reach of observations. And some examples of this amplification mechanism are, for example, the very long travel time of particles and signals in general that come from astrophysical or cosmological sources. This is such a huge distance that can make up for what you mean by being at lower energies. Other kinds of amplification mechanisms can be experiments that manage to reach an extremely high sensitivity so that they are able to see even into very tiny modifications of standard physics, or interactions where the characteristic boost of that interaction is very large, so that also brings you somehow closer to the Planck scale. And all of these, and you can think about other things. But this is what makes us hopeful that eventually we can get to turn quantum gravity into an experimental research. So we say, okay, fantastic. So I get my favorite quantum gravity theory. You pick one from the box that we learned from in the lectures very much. I just compute whatever is the prediction for an effect that is being measured, and I just measure the parameters. Well, it would be very nice, but the unfortunate fact is that none of our full-fledged quantum gravity theories are capable to make rigorous predictions about what we would measure in an experiment. This is because very often they are very complicated theories. We are only able to do computations in some very specific limits, so we're taking some simplifying assumptions. For example, we talked about the symmetry reduction before quantizing and so on and so forth. So it is not such a trivial matter. So there is another approach that you can take. So you cannot just go from your theory to the experimental prediction. But what you can do is work at two levels, one that I call bottom up and one that I call top down. So the bottom up is to just construct some effective models that you think might contain some features that are reasonable given what you know about your general quantum gravity theories. And your guiding principle is that these effective models are testable. So that you can compare that to the two experiments. The other approach is what I was mentioning earlier, to start from your quantum gravity theory, work out some semi-classical effects, so take some simplifying assumptions eventually, or if you disregard argument, then you can do this at different levels of rigor, and try to link them with the phenomenological models that you build on the other side. So hopefully these two lines of these two approaches at some point touch, so at some point they connect one with another, and based on the phenomenological, on the constraints you get in your phenomenological model, you are able to constrain classes of possible quantum effects and inform that these effects, how these effects should appear in the full theory. So this is the spirit of quantum gravity phenomenology in general. And some here is just a brief list of some possible effects that have been considered in these effective models. So departures from Lorentz symmetries, fuzziness of space-time geometry, which might have effects on locality, for example. Departures from CPT symmetries, violations of the equivalence principle, or violations of the quantum mechanical uncertainty relations, for example. These are all just phenomenological models. And then, okay, you're happy again. So you were set and you were happy. So you were happy and you were set, now you're happy again. And say, okay, fantastic. So for example, I can decide I want to study violations of Lorentz symmetry. This will affect the time of flight of particles from astrophysical sources. So I can just look at this, and if I detect the delays, I have a constraint on quantum gravity. I can say, for example, I see a time delay, and I say, this is a proof there is quantum gravity. And unfortunately, this is again not the case, because this kind of analysis is really full of many subtleties from the theory side, from the phenomenological side, and from the experimental side. And you really need to know all the sides of the story in order to be able to make claims or to produce research that is really valuable and is going to give us, going to produce progress. And so this is why we are here, because in order to start understanding all the complexity of this kind of analysis. Now here, I'm just going to give you an example of the kind of complexity you encounter from the theoretical side. So when the experimentalists at some point tell you that they are seeing something, and then you want to understand what it is. Tomislav later is going to talk more about the experimental side, and I'm sure that he will also convene the message that also on the experimental side things are really complicated. So okay, so let's go and see what this is about. So my example in particular will be about Lorentz symmetries. So about another already mentioned this briefly. We can imagine that because of quantum gravity, we have departures from Lorentz symmetry. Well, in general, we have three options. Either nothing happens to Lorentz symmetries because of quantum gravity, which is an option, or at some point Lorentz invariance is broken, or relativistic invariance is not broken, but the kind of the Lorentz transformations of the target form. And I will explain this better in a second. Anyways, these are different options. So let's say that you are studying modified dispersion relations. Still, you need to understand within which framework you are studying that. It's not just, okay, there is a modified dispersion relation, and that's it. And not only this, then you need to specify the theoretical framework, like what are your mechanical assumptions, your dynamical assumptions. For example, do I have access to a Hamiltonian description of my model, so on and so forth. So, I mean, it's not just saying there is a modified dispersion relation. You need to say many other things in order to understand what model you are constraining exactly. So, let's take an example, a case study, and let's assume that at some point in the future, we are able to state with some certainty that the time of arrival of massless particles that come from astrophysical sources depends on the energy of the particles because of Planck scaling. Of course, and this is here I'm hiding all the complexity of the experimental side. But this is not this is not at all a trivial statement to make in a robust way, because you have to consider many other options. For example, deciding due to intrinsic effects at the source, or I don't know, you might have to take into account of other kinds of observational limitations. You might have to deal with a very poor statistics, so you don't have very good data, and you need to get information. You need to find a way to get information from the data you have. So all of these is something that needs to be done, but the way to do it at best is to know what kind of physics you're looking for. And I think this message was already conveyed a bit today, and in the statistics lectures before, and it will be emphasized even more in the following lectures and so on. But let's say that we are, after many efforts, we are able to say that this effect is here, and this effect might show up, for example, in this way. These are the kind of very preliminary analysis that also Jose Manuel mentioned. So this is the kind of arrival of very high energy photons from GRBs, and you might see that their time of arrival has an energy dependence of this sort. By the way, in a very simple scenario, just to give you the order of magnitude, to give you the idea of the orders of magnitude we are talking about. If this was a Planck scale effect, we would expect that photons of hundreds of GeV would have a time delay for advanced, well, a time difference with respect to low energy photons of seconds, few seconds, fractions of a second. So it's a very tiny thing. But anyway, let's live in this happy world in which we actually saw this effect. And even you might see some indication comparing the time of arrival, not only the photons, but also you could at some point have indication that also very high energy neutrinos follow this kind of behavior. And again, just to give you an order of magnitude idea of what you're talking about, because the neutrinos are much more energetic. Here we're talking about tens, hundreds of TeV, so several orders of magnitude more. If there was an effect at the Planck scale, the difference in arrival with neutrinos and the low energy factor of the signal would be weeks. So in this case, there is additional difficulty of saying, how do I match this random neutrino that arrived to some signal that came in the photon sector with slow. This is part of the experimental complexity. But anyways, let's say that we can do this. And how do we model this? We say that the time delay, delta t, is proportional to some coefficient, and then proportional to the difference in energy between the high energy and the low energy particles, the travel time, and over the Planck energy. And notice here, for example, that this is one of the effects that I mentioned that has a big amplification factor given by the distance that was traveled. So let's assume that I am able to say, okay, there is this effect, and I can even put, I can even say how much is eta. So if this was true, this would be the value of eta. Okay, very nice. What can I say about the theory of quantum gravity? And now things become complicated. So first of all, you say, okay, there is this time delay. In order to have a time delay, I need to have an energy-dependent speed of propagation for the photons or for the neutrinos, whatever. From here, I can say, okay, if I make another assumption, for example, that the velocity is computed in the usual way, then this time delay can be ascribed to this famous modified dispersion relation that is of this kind. Here you have the modified term. So here you see that you already made several assumptions that they don't need to be, I mean, you could have used other assumptions. So here already you are making some assumptions. But still, so you get, say that you get here, you think these assumptions are reasonable. Then I mentioned before that an NPR is what that some departure from Lorentz images. But still, can you say from here whether you are in the Lorentz breaking or in the Lorentz deforming scenario, for example? From here you can't. I mean, you would have, this wouldn't change in the two scenarios. So this doesn't tell you much about what your quantum gravity theory should look like. You need something more. And okay, before I go on, let me explain a bit better what is the difference, because this is like crucial between these two scenarios. I am making an example about the modified dispersion relation because in fact it is one of the most promising signals that we are looking at the moment. So it is interesting to try and understand it more. So in a Lorentz breaking scenario, what happens? It happens that the transformations that lead different inertial observers that are Lorentz transformations, special relativity, they work as usual. So you transform between one observer to a boosted observer with your usual Lorentz boost. What happens is that there is a preferred reference frame. For example, if I go to the modified dispersion relation here, this dispersion relation will only look like this in one reference frame. If I change reference frame and the energy and the momentum transform as usual, just the computation is very easy. You get a different dispersion relation in a different reference frame. So, which reference frame are we measuring this dispersion relation? Some people say, okay, the natural frame will be that of the field, but this is also arbitrary. In the other scenario where you're not breaking Lorentz invariance, so this is why you're breaking invariance, because physics does not look the same in different reference frames, which is the principle of relativity. In the other scenario, you preserve the principle of relativity, so physics looks the same in all reference frames. How do you do that if you have a dispersion relation that is not the one of special relativity? You need to change the laws of transformation of the energy at the momentum. So you need to change the action of the Lorentz boost at high energies. And in this way, you can make, for example, if I take this dispersion relation that is the same as before the mass, you see that the energy can transform as usual, but then the momentum has to transform in this nonlinear way. This is one option. So you need a compatibility between the laws of transformation of energy and momenta and the modified dispersion relation you would like to preserve. And these two options here have implications that can help disentangle them once you see that there is some modified dispersion relation. So what happened in the first case, so the Lorentz breaking scenario, so you, again, we assume that we know that there is a modified dispersion relation. In this Lorentz breaking scenario, you can still have, for example, that in interactions, the energy and the momenta are conserved as usual. So the sum of the energies you had before an interaction is equal to the sum of the energies you had after the interaction, and the same for momentum. Of course, if you put this together with the modified dispersion relation, and this is something that Jose mentioned before, so let's assume that the photon has this modified dispersion relation, and the electron positron have the same thing, but just with a different parameter. Here is psi, and here is eta. There is no reason why they should be the same. You could have different dispersion relations for different particles. So assume that these are the dispersion relations, and assume that this is the law of conservation of energy momentum. You can work out what is the constraint on the decay of the photon, and you find that the threshold that you have is different from the one you get in the standard special relativity theory. And of course, this kind of effect is already quite strongly constrained by observations of the rays. So if you see a modified dispersion relation and you work out the constraint of the parameter beta, you have to check whether this constraint is compatible with the constraint you get, for example, from the photon decay. Another thing. So there in the previous slide, I was making an assumption about other features. I was assuming that everything else was standard. But things get more complicated if I want to embed this Lorentz regulating model within, say, an effective theory framework. Then you get your standard model extension Lagrangian, you work out, you work things out, you work out your modified dispersion relation for the photons, and you discover that if you want to embed the modified dispersion relation within the standard model extension theory, then you necessarily get that photons with different density would need to have different corrections, different size for the corrections to their dispersion relation. So this is another constraint to take into account if you want to do the analysis within this other theory. And how this show up in your analysis? One example is that you would see that the systematic dependence on the time of the energy of the time of arrival would only happen if you have circularly polarized source. But if they are linear, that would have a combination of advanced and delayed signals, so you would not have a systematic effect of this kind. Or and moreover, from here you work out that if you have a linearly polarized signal, the direction of this linear polarization will rotate when the signal propagates. This is just comes out from putting your dispersion relation into the phase of the radiation field. So you can check whether sources that produce polarized signal show this kind of effect. And this is also an effect that is quite strongly constrained, for example, from observations of the Corfu nebula that is polarized radiation. So again, you would need to see whether the constraint on the modified dispersion relation that you got is compatible, for example, with this other constraint. Let's go to the other. Well, so as you have seen already within the Lorentz breaking scenario, doing a thorough analysis is already quite complicated. Then there is the additional complication that that's not the only option available. As we said, you could have a scenario where symmetry transformations are default, as I explained before. What does it mean? So as I mentioned, you need a compatibility condition between the dispersion relation that you have and the action of the boost. So if I transform this dispersion relation, I just act with the boost on the energy and the momentum appearing in the dispersion relation. You can verify that this is not satisfied by standard transformations and that you need the form transformation. This is what I showed you before. What happens? So what does this imply? If I have this deformed laws of transformation of energy and momentum, and I still want not to introduce a preferred frame, I also need to modify the conservation rules in interactions. Because if I now apply this kind of deformed Lorentz boost to the standard conservation laws, they will not be provided. So again, if you would be introducing a preferred frame, it would only be true in one reference frame. So you need to also modify the conservation laws in such a way that they are invariant. And well, you don't need to read this formula, just to show you how you can do the computation. And for example, you can find that again for that modified dispersion relation and for this kind of Lorentz boost that is compatible with this dispersion relation, one compatible conservation law is this one. This is not unique, but it is one option. And you see here that there are modifications, again, proportional to beta. Well, this should be over the Planck energy. Sorry. But you see, here you have this modification. And of course, now that you have done the analysis for the Lorentz breaking phase, you already know that you have to go and see what does this say about constraints coming from, for example, interaction thresholds and so on and so forth. And this gives you a powerful way, for example, to distinguish the two scenarios. Because if you go and do the computation for the threshold reactions in the same way that we have seen for the loop case, I'm not going to do it here because it takes a while. But what you will get that the constraints that you would have gotten in the lead phase are much weaker in the other case. And for example, all the processes that are usually forbidden in special reliability, because if they happen, they will be produced a different frame. They also do not happen in the DSR scenario, just for the same exact reason that it is a scenario where you do not introduce a preferred frame. And if you actually do the math, you will see that that things work. So from this point of view, the strong constraints that you get from looking at modified interactions in the Lorentz breaking phase are not so strong as constraints. These constraints are not so strong in the DSR case. So you have to take this into account when you are evaluating how the different models are doing. At the level of these DSRs or of this deformed special relativity scenario, the model building is still not at the level of being able to do a dynamical analysis as the one that I discussed in the context of standard model extension. So this is something that needs to be done in order to be able to do more precise statements. But anyway, the fact that you have modified conservation rules is already telling you that this is a framework that is not possible to embed in an effective field. You have to embed it into something else. We don't know what. Okay, so I finished here. I hope that I scared you enough showing you how complex is arising. But I mean, I hope that I didn't only scare you, but I also gave you motivation to really try to understand things better. And so I leave you with this citation, which is just saying that when we are not understanding something, we start inventing theories, but then at some point the true discovery will happen when the theory and the experiment work together to produce something meaningful, and that's what we should aim for. So, thank you, and I give the word to Thomas, unless there are questions.
Okay, so hello everybody. My name is Tomislav. I will tell you something about experimental aspect of what we're just talking about. And I will focus on gamma rays because this is what I do and I feel most comfortable. Now, Julia mentioned my name quite a few times, and if I wanted to do everything she just promised I would do, it would take me a few hours, but not this time. So I will say a few things, what Jose Manuel already mentioned earlier, with a bit more details, but not too many. Actually, what I want to do here is motivate why you are listening to some of these lectures these past few days. Why the statistics, why we talk about the sources of cosmic messages, or the propagation, things like that. And I will show some problems that we are meeting. This is the outline of my talk, but basically I will focus on what we just said. So motivation for our research is, of course, we want to see if there are some effects in addition to those that we already know. And of course, we turn to cosmic messengers because they reach by far higher energies than what we can accelerate them to in man-made accelerators. Still, these energies, these are the highest energies we have detected so far. I think I forgot to update this one. I think we 1.2, yes. Still far below Planck scale, so we had to do some other things to test quantum gravity models with what we have here. And this is where we usually start. Of course, I'm starting with modified exclusion relation for gamma rays. If you're working with neutrinos or cosmic rays, you will do something similar. So I'm just taking this as an example. I think you've seen this already a few times in one form or another, but it's more or less always the same. So these are the modifications we are looking for. Usually we are looking for n equals 1 or n equals 2, which we usually refer to as linear or quadratic contribution or modification. We put this somehow in analysis, trying to see whether we can measure this EPG and the energy at which we expect these effects to appear. So, what are the consequences once you introduce such modifying term into the dispersion relation? Well, there are collateral consequences, and I will go through some of them and show you briefly how we try to test this. So the first one, historically, the first one that was tested and somehow where it all started from, and maybe the first one that comes to your mind is that if you modify the photon dispersion relation, the photon group velocity will not be C anymore, it will be something else. Depending whether this S is +1 or -1, these new photons will propagate through vacuum either faster than the speed of light or slower. And this effect is very small, of course. So another reason why you can't do this in laboratories. You take gamma rays, which have much higher energies, and in addition to that, they're emitted from some astrophysical sources, which means they travel billions of light years to reach Earth. And you hope that that is enough for this effect to accumulate enough that we detect. And how do we go about that? Julia already mentioned that basically you take two, well, you don't really take two photons. It's just an example. You have two photons, assumingly emitted at the same time from the source, and you measure the the time and detect them, and you see whether there is any difference. Of course, if they all travel at the same speed, they will reach the detect them at the same time. Of course, you have no idea whether these two photons were emitted at the same time, because they're halfway across the universe, so you don't really know what's going on in the source. So you do different analysis techniques. There are several. I will focus on the most popular one, at least among the experimentalists, which is maximum likelihood method. You can also find other methods in the literature. If I had more time, I would also present them, but I will focus on this one. I will also not go into many details here, just a rough description. This is a probability distribution function for detecting an event, a gamma ray of energy EI at some moment t pi. But, and here comes everything we know or think we know. Let's start from this side. This part here says we here put information about our detectors. So this is energy resolution and energy bias in our detections. This is acceptance, or what we call effective area, meaning probability of detecting a photon, any of that energy. So we very much like to put what we know about experiment, about our instrumentation into this PDF. Then we put in the energy distribution of events or spectrum or differential flux, that was already mentioned today, and some additional propagation effects. Most notably, this is the absorption of gamma rays on background light. And of course, this is the spectrum. Well, in the way it's written here, this is the spectrum at the source, so it's in the spectrum. And then this is a line curve or a temporal distribution of events at the source. Here we introduced this delta t as this time delay in arrival caused by this eta here. This eta is some parameter we introduced that represents Lorentz acceleration, and we introduced it like this because it's around the order of 1, so it's easier to do manual calculation. Of course, we don't really know what this is. We don't really know what this is. By multiplying the energy distribution of events and temporal distribution of events, we assume that they are mutually independent, which we also don't know whether it's true. So we make a lot of assumptions. You have to start from somewhere. The thing is, present-day models of how the sources emit gamma rays are not precise enough to put the exact let's say, formula which says this event was emitted at that exact time. We simply don't know that. Probably will have models which are precise enough to tell us that. But we start from what we know. Now, and so this is the probability distribution function for one single event. And then you collect all the events you have in your data set. And then you minimize this likelihood for this parameter eta. And this is your Lorentz solution parameter that you want to get out. And this is kind of this maximum likelihood method is a very well known and very well studied statistical analysis method. This is why we wanted to take this course on statistics these days, but it's very well studied. However, once you start really using it on a specific example, specific data set, it gives you a lot of headaches. it's not that easy to implement, to work with it. You start questioning your life choices, doubting everything. But once you get through that, you have to be alive. What do you get out of it? You get something like this. Not much to look at. This is a particular example. I don't know whether you're familiar. Some 2 years ago, Magic Telescope detected a gamma ray burst. This was one of the first gamma ray and one of the only gamma ray bursts detected with Cherenkov telescopes. There have been only 4 so far, unless I forgot one. And for the first time, gamma ray burst data observed with Cherenkov telescopes was used for LIV study. All the studies before gamma rays were performed on data from satellite detectors. So in this one, we reached much higher energies, which is a plus. However, this here is the Likert. This here is the flux of this gamma ray burst. These points here, this is what we measure with Magic. Everything else here comes from measurements in lower energies and from theoretical modeling of what we expect how this emission look like from this gamma ray burst. So there is quite some assuming in there. And so we put everything more or less back in here and get something like this. However, as an experimentalist, I want to point out that this is usually, well, it looks like the job is done, but this is usually a smaller part of your work, of your job. The next part is estimating bias, estimating confidence interval. For instance, if you check this, here we estimate this parameter eta. And if there is no LIV, so if everything is business as usual, then this should be centered at 0. But you can see that it's not really at 0. Actually, it's quite far from 0, especially, well, here not so much here in this linear case. So did we detect LIV? How do you think we felt when we saw this? Were we happy or something else? I was scared. I would like to say how scared I was, but it felt like. I was trembling. Because you see an effect that everybody wants to see. And you know that it's probably not correct. So what do? Well, always when you whatever the experimental research you do, you have to test for your resolution or uncertainties and bias. And this is actually in experiments major part of your work. You create a bunch of Monte Carlos. You repeat the same analysis on this bunch of Monte Carlos. Then you do distribution of those results. And you see also that these distributions are not centered at 0. So obviously your analysis has some bias. Now, bias is of course not good. Also, large uncertainties are not good. Uncertainty is basically this here, more or less. But as long as you understand where your bias is coming from, as long as you can estimate, then you can subtract it from the result. That is a good thing. That means you know your experiment, you understand your results. Once you do that, once you correct this with this bias, then actually I think this was already corrected. Then it came closer to 0, so this is a given 2 sigma, so it's fine. I think it was much further away. But I would have to check the original paper. I forgot about the numbers. But anyway, once you factor this in, then you get a conclusion that you see no LIV effect. And then, okay, I can't say that you're happy then. Of course, it will be much more exciting to detect it, but you have peace. Mostly you have peace because you understand your results and you understand every section of your result, every part of your analysis. Of course, it would be nice if this turned out to be centered at 0 and this was very narrow. Then it would mean that there is no bias and that we have a high precision analysis and that we actually see some effect. That would be, let's say, most exciting scenario. But what I really want to relate here is that this is a very important and most time-consuming part of the job. And very important, of course. Only after this can you really say you understand your results and interpret them in that way. Okay, so next effect, we already heard quite a bit about it. This here you can see is the distribution of extragalactic background light, and you already see that gamma rays are scattered on this extragalactic background light into this channel. What happens as a result? The spectrum is attenuated. This is from another source that we detected some time ago, and you can see these black points is what we mentioned. But then, since you know that this effect happens, and you know more or less the distribution of this background light, then you can use this knowledge to what we call deabsorb those spectrum. So you can calculate what you expect the spectrum look like at the source, and you get this blue spectrum here. So original source intrinsic spectrum. However, if the dispersion relation is modified, then this does not happen quite the same way. And you can see here, this is a plot that we recently published in a review paper, and Jelena prepared it. She's right there, so you can ask her about the details. But basically, this is what happens with this reaction if you allow for dispersion relation to be modified. Because if you do that, then the energy reaction threshold changes depending on whether your photons, your gamma rays are superluminal or subluminal. One of these two scenarios would happen. If the gamma rays are superluminal, then the threshold reaction will be even higher, more difficult to, sorry, am I saying that right? Lower. Yes, I will turn around. And your spectrum will be, this is, let's say, original intrinsic spectrum, assumed. And if your gamma rays are superluminal, the reaction threshold will be lower. It will be more easier to reach this threshold, and the attenuation will be stronger. Now, this is something that is difficult experimentally to test because it's difficult to say whether this happens because of superluminal photons or it's some intrinsic source of physics. However, if your gamma rays are subluminal, then the threshold becomes higher, and it's more difficult to reach the reaction threshold, and the absorption will decrease. So what will happen with your observed spectrum is something like this. And how do we try to find this? Here you can see again the same distribution distribution of background light. The colors are a bit messed up. It's much prettier. This is what happens. This is this attenuation effect parameter or that, and this is actually the attenuation effect. So this is how they change, and this is only for subluminal gamma rays. Basically, this is what happens with your attenuation. This dashed or dotted line is here, black dashed line. So this is what will happen to your spectrum. However, if there is some level of quantum of one-to-one relation, then you will see either one of these effects depending on how strongly is valid. And this is an example of some real data by the Haskell collaboration. So these points are the measured points. This blue line, black line is what they fit to their data, so observed spectrum. And what is expected to happen is something like this. Or rather, you do this deabsorption. We don't know what the explicit spectrum of our source. We only know what we see. So what do? You do this deabsorption. You try to guess what is the intrinsic spectrum of your source. And you do this for different values of EQG. Now, at some point, when EQG becomes low enough, this deabsorbed or assumed intrinsic spectrum will develop this upturn here. And here it becomes important to know your sources. That's why you're listening about this. Because this behavior is considered to be non-physical. This is not something we expect in our sources, especially in active nuclei, which I use in this slide. So basically, you do this deabsorption. So you go from here through here, and you do that for different values of EBL. So let's say you start from here and you decrease. And as you decrease it, you will get one deabsorbed between the other and the other and the other. At some point, you will reach here. And once you reach that, it will be clear that you have to solve. Because now you're seeing something that you don't expect from this source. This is why at least one argument why it's important to know your sources. So you can say at some point, okay, we know that this is not happening in our sources. Or maybe not know, but we are very certain. Again, these are the plot. These plots were obtained through maximum likelihood, although this time not for this time delay, but for this deabsorption. There are, of course, one point to note also here that see these uncertainties on the measured spectrum are quite important because if you do this deabsorption, sometimes you can fit, or if these are too high, rather, then you can fit a whole bunch of stuff on these second points. It's not very helpful. Of course, need to be taken into account. This same data set used here. This is the spectrum that you have seen, and this is the light curve, so flux. And this on this data set also this study time delay was done. This is the first time when both study on time delay and spectrum deabsorption were done for DLIV. And you can see here and compare the results. So for lower limits on EQG from time delay and from universe transparency. You can see that these are 1 to 2 order of magnitudes higher. These limits coming from universe transparency. question about this a bit later. The other effects, I will not go through them in so many details. Photon decay and photon splitting, you already seen that mentioned today. These are basically, if you allow photons now to be superluminal, they could either decay or split. And this is the effect that you would expect in that case. Basically, photons of higher energies would disappear from your spectrum. And depending on whether you see that in your spectrum or not, you can set limits on your on EGG, on LIV energy scale. These are the plots from Hope study done last year, but also LASSO after detecting that 1.4 peta electron volt gamma ray did their own study, and these are the results, the most stringent ones and also the most recent ones. Another study very interesting today. Also, you heard some talk about the atmospheric showers from gamma rays and cosmic rays, and this can also be used to test LIV. If you allow for dispersion relation to be modified, then also this Bethe-Heitler process, that is the cross section, is modified. To modify the cross section, the dynamics of interactions, then it will be less likely for a gamma ray to interact with atoms or nuclei in air. And since it's less likely, it will slow down the development of showers, or rather, showers will develop deeper in the atmosphere. And as you heard today from Alisa, you put your detectors at some height, and you actually make them focus on, if they are checkpoint telescopes, they focus on, let's say, 10 kilometers above ground. But if your showers develop below that, they will not be detected. And again, you will be missing something in your observed spectrum. So using that, again, you can set constraints on the gravity energy scale. There are other effects which are not really tested on gamma rays, like synchrotron radiation, quantum scattering, vacuum birefringence. This one I'm very sorry about that we cannot test it. Simply with high energy gamma rays, very high energy gamma rays. For this, you need to test to measure photon polarization. And we cannot do this in high energy gamma rays, very high energy gamma rays. There was this AMIGO project that was mentioned after that, which was proposed, and this proposal, the detector could in one mode measure gamma ray polarization. Unfortunately, existing instruments cannot do it. And in particular, charcoal telescopes, this is not some technological, this is simply nature preventing us from doing it. If we wanted to measure very high energy polarization, gamma ray polarization, we would need to know the plane in which this first electron-positron pair is created. And this is impossible to tell from our data, which is too bad because we could set some real strong constraints to this effect. But okay, if AMIGO or AstroGamma or any similar project is realized, we can use that. So far, it's been done on optical and X-ray. Here is a brief comparison of these different effects, or rather of quantum gravity energy scales of these different effects. So these mind the units here. This is for linear modification, for quadratic modification. and this is for time delay. Then EBL absorption, you can see there are some bit more stringent limits here. Again, EBL absorption. But look here, look at this constraint from photon decay and from photon fading. I put in this today with very little sleep last night, so I might have missed a 0 or added 1, but it's not important at this point. You can easily find the original publication and check it for yourself. The point here is to show this value in comparison with these ones. Now, my question to you is, what do you think? Does this mean that there's no point in doing this studies anymore? Because this limit or this exclusion is so high, there's no point in doing these studies here. So orders of magnitude lower. To make it easier for you, this is an ongoing discussion, so there is no correct or wrong answer. I just want to hear your opinion. I have my own, and I can tell it to you later. But I would first like to hear you. Anyone? I think we agree. I'll just formulate this from my perspective. In the beginning, when I showed you the modified dispersion relation, maybe I didn't say it at the time, but this is not, I think Julia said, it's not a consequence of any particular quantum gravity model. It's just something that we use to test anything. And if we detect, if we measure this variance relation, it will not mean that some particular model of quantum gravity is correct. It will just show us that there is some effect, and then we'll need to do many more different measurements to investigate the origin of this effect and to describe its nature. But until we detect it anyway, we don't really know where it's coming from. We don't know whether the same effect is responsible for subluminal or superluminal photons when we talk about their velocity and whether this effect is the same, their interaction with other photons or with electrons, positons, or atomic nuclei. So my point, my opinion is, yes, we continue testing whatever we can. Maybe one effect exists and other doesn't. We don't know.
Particularly in ESR, for example, decay and
already coming from models, we know that some are positive, some are, depending on the model. One thing I would very much like to promote is this LIV consortium, which is composed of researchers from 3 chemical telescope collaborations, HESS, MAGIC, and Veritas, and we join together to merge our data and do time delay LIV tests on a joint data sample. There are several reasons for this. First of all, we get larger statistics, much larger statistics, more photons and more sources, and more different types of sources. Having different types of sources is important because this enables you to sort of exclude source-dependent effects, source-intrinsic effects. On the other hand, it's a preparation for the chemical telescope array, era because we are combining different instruments, combining the instrument, what we call instrument response functions in the description of our instruments. And in this way, we are preparing for upcoming of CTA. We have first paper which describes the method and which is based on simulations. I expect it will be submitted next week or the week after that, so very soon. And then after that, we plan to start working on a second paper, which will be done on real data and see how that goes. Anyway, in the annual conference next week, there will be a talk by Daniel Terzić about this consortium and this first part. CTA was already advertised several times. In addition, I would also like to say that Magic also observed another gamma ray burst end of last year, end of 2020. This analysis is still ongoing, but there is one very intriguing thing about this GRB, that it was estimated that the redshift larger than 1. So this, if this is true, this means that this is the first source observed with giant telescopes at redshift higher than 1. And this will strongly constrain, especially time delay. But as I said, the analysis is still ongoing, and we have to see whether it will be useful for relative time. Also, when I showed you that GRB earlier, you've seen that all the data are just on the line here. Actually, it's a power of decay, and well, there's nothing much you can do with this. We hope to detect gamma ray bursts from the beginning, so to also detect the maximum. This will give us a much stronger handle on the data set to investigate. Okay, so these are just some takeaways. I think the future of this research is looking bright with the CTA, so I would invite you to join the party. Thank you. There are different ways of doing that. Some of them you can use, you can treat as nuisance parameters. Others, when possible. When possible, I mean sometimes you know the range of these parameters. So that's of course just information. Second is how your analysis will run if you use those. Sometimes it just takes too much time and it's not feasible. If you cannot treat it as nuisance parameters, then you fix them, but then you do this part. You repeat your analysis on bunch of Monte Carlos, and you did Monte Carlos, and you create that, you change these parameters. And then from that, you estimate. Does that answer the question? Yes. Yes. If this is 1, let's say, if it's just a straight line, it will be perfect resolution. then of course you also have at least the probability of detecting an event of some magnitude. But basically, if this is a straight line, then also you don't need. Yes, but you never know exactly. That's exactly. I have a question for you. What do you expect to get from this school? Or rather, when you come home, when you go home, what do you plan to do? Business as usual? Do what you did so far? Or do you plan to somehow interconnect? So if you're a theoretician or the phenomenology, do you somehow planning on connecting with experimentalists or the other way around? But don't just nod. I mean, don't tell me that. Right?
Well, I have a remark on that. This is assuming that the connection is of depth one person, right? But usually it takes a lot of intermediate person that collaborate to get from one to another, right? So
I agree. Okay, let me reformulate my question. If you are a theoretician or a phenomenologist, do you have some problem that you would like to have an experimentalist or experimental group to tackle? Or if you're an experimentalist, is there some input that you need from some theoretician? You don't have to answer now, it's your homework. Come on, it's a school, you have to have some homework. You can email it to me, let's say by Sunday evening, and then next week we discuss it. We have discussion sessions, so yes, email me your answers. I'll give you an example. My case, so maybe triggers you. Christian here published a paper a few years ago where he introduced something like this, not quite like this. Christian, would you maybe like to expand? You will say it more correctly than I do.
Any assumption, so I looked at the general communication without any assumption on independence
and also not in necessarily flat.
Yeah, on a homogeneous topic space. Like calculate formula, there is a pre-function, this motivation function, which is not necessarily polynomial. And the question still is what to work on that.
Yes. So we talked about this.
We can, without putting any assumptions on the form of the motivation, we can generate response on this. Or if it is necessary for comparison with experiment to assume specific functional form like the polynomial form. It's not giving me from the experiment how you do the data analysis, because from the theory side we can do a calculation quite general, but then there is an unknown function inside. The question is, can you constrain this function or the functional form in general?
Right. On my side of the story, I read the paper, I understand what you did. I have no idea how to use it in my analysis. So this is where I need your input to translate your result. Put, let's say, here.
Yeah, and I need to know what exactly this shall represent.
Right.
How I need to transform the result with this general function so that we can put it.
Right. And actually, this LIV, okay, we will discuss it next week when the other members of LIV are here. So this is an example of what we want to do today. We didn't plan it from before. We just met a year or two ago and started discussing and this came up. But think about it. Is there something that you're working on and, well, you don't know what to do with it, but maybe if person from the other side of the canyon took a look at it, maybe it would be clear to them. I guess no need to reply now, just think about this. This is the point, one of the points, key points of this podcast. Which one, what we want to do here, start this kind of collaborations. Okay, I think I'm done. Thank you very much.